Out of the topics of ecology, flow of energy is probably one of the more important ones in retrospect to regarding how energy flows through an ecosystem. We have to know the difference between food chains and food webs, which is very, very, very simple, but nonetheless it's important to make sure that we understand the difference between the two. A lot of the things that sometimes people get wrong is reading or understanding the arrows in a food chain or food web, and not understanding that the arrows are telling you the direction that energy is going, and not he consumes this thing that the arrow is pointing at. And then I'll talk to you a little bit about biogeochemical cycles, in particular water and carbon, which are very, very, very essential for life. Now, throughout food chains and food webs, there's a question that I want you to keep on the back of your mind, and it is why we refer to the energy that's transferred in an ecosystem as an energy flow, and why we don't refer to it as energy cycling. So throughout all this, keep that in the back of your mind, why we refer to that transfer of energy as energy flow and not energy cycling. Even though there is a set amount of matter on the planet, and matter, obviously you learned long ago, hopefully, that matter can't be created. So we have the number that we have, and that's basically it. That's not going to change. Matter can change from one state to another, from one form to another. So if energy is changing from one form to another, why don't we refer to it as recycling energy, or cycling energy around when it changes from one form to another? And we do refer to it as flowing from one form to another. A few words that we need to know, which are very, very, very important. Herbivore is that plant eater. Carnivore is a consumer or an organism that obtains its nutrients from another organism. Doesn't necessarily have to be living, but it does have to be a meat eater, what we typically refer to as flesh and blood. The omnivore is the one that does both, that eats meat or other organisms, and eats plant or derives its energy from plant as well. And then you have the tridivore, the consumer that obtains its nutrients from detritus, the undissolved material from the decomposition of organic remains. Okay? An example might be like a dung beetle. For example, he's getting his energy from the organic remains of the waste material from an organism. Sometimes people thought like a vulture would be one, but he's not. A vulture is a carnivore because he's eating meat. Okay? So, detritivore is there's certain bacteria that classify under that, fungi that classify under that. But in terms of another organism, like a moving around organism, because bacteria is an organism, the dung beetle is a good example of that. Food chains are a chain, basically a unidirectional pathway that shows a relationship of feeding from one to the other. Now, I refrained from using the word organism because food chains begin with the sun. All food chains begin with the sun. And from there, you have your producer, who is basically deriving energy from the sun, and from there, you have your various levels of consumer. But it all goes in one direction, unidirectional. there is an end to a food chain, and eventually that food chain can cycle around, but it will not cycle completely back around because we don't provide energy back up to the sun. But it will go back to here, to this level of the producer, to the level of the producer. So you have your energy, which starts at the sun and is going to start off as solar energy, and then it's going to move to the producer, and from the producer, this, which is your largest level of energy, is going to give energy to your first consumer, your primary consumer. Your primary consumer will always be a herbivore because he's eating a plant. Okay? Now from that point on, then you're going to have your consumers, your carnivores, from that point on. And in the end, we'll get to it in a second, but you get your apex predator, which is your top level consumer. Basically, food chains end, for the most part, they end at the apex predator. Now, a food web, however, is not in one direction. It takes off in multiple directions. You're still going to get energy in the form of the sun to planktons and so forth, microscopic organisms that are consumed by larger organisms like fish. But even these themselves will give energy toward larger marine life. And the other difference with a food web is that you don't have one point of origin. In a food chain, you do have a point of origin, but in a food web, you do not. So it's known as a network that is a series of interrelated food chains. You could derive food chains from a food web. You can't do it the other way around. I know I'm beating a dead horse with this, and I know I'm sounding redundant, but I want to make positively sure that you guys understand. The arrow is showing what? The arrow is showing the flow of energy. So when you see an arrow pointing toward this fish, it doesn't mean he eats this fish. On the contrary, he is giving energy to this fish. The arrow is showing the direction of energy. We know that this lobster is not going to eat this large fish. It is the other way around. So if you always make sure that you remember that, that's, relatively important. Now, how does energy flow within ecosystems? All right, so I'm using the same pictures, but again, remember the prefix troph? That's what they're referring to here as trophic levels. So I want you to understand the terminology of trophic levels. What would be your first trophic level here? You remember, think back to what trophic, meaning trough, which would be to swallow, right? All right. What's going to be your first trophic level here? We're on a food chain, so this is the way energy is flowing. Your first trophic level is going to be your producer. And then from there, you need your second trophic level, which is your rabbit. He is always going to be your what? A herbivore. Okay? Now, after your second trophic level, you have your third trophic level, because he's the one that's going to eat this bunny, and then your fourth trophic level. One thing to keep in mind, if an organism in this trophic level was able to surpass this trophic level and go straight to this one, could it? Yes, it could. Okay? It doesn't necessarily mean that if this animal right here, this eagle, or this large predatory bird, doesn't necessarily have to go this way. Excuse me. Doesn't have to go this way, and then and can only eat organisms in the third trophic level. He also has the opportunity to eat something from the second trophic level as well. All right, some more. These are basically the same thing. But it's also given like as a different word. We just went through that first trophic level, second trophic level, third trophic level. Also understand that it could be referred to as primary consumers, secondary consumers, tertiary consumers, and you can have quaternary consumers in a fifth and a sixth and a seventh and so forth. The reason why I'm giving this to you is so that you also understand this term, apex predator. Your producer is usually your plant that gets its energy through solar energy, through photosynthesis. From there you have your primary consumer. It's going to be the herbivore that eats the plant. Your secondary consumer is going to be the carnivore that eats the herbivore. And then you can have a longer list here of consumers. But you need an end. To that food chain, you need an end. And there's where you get your apex predator, which is the carnivore that has no predator that are going to hunt him down. I was talking with first period today. Lions in that environment, in that ecosystem, are apex predators. But does that mean that no other consumer can eat a lion? Well, yes, of course they can. Hyena have been known to kill and eat lion. But would they do that with an adult, lion? No. They would only go after what? Its cubs, the young. So, yes, we can say technically that hyena could eat lion, even though the lion is the apex predator in that environment. But he would only do it, again, if given the opportunity and under the right circumstances, which means that he's going after the young, not the adult. Okay? For the most part, your apex predator is the top of the food chain, the one that nobody hunts him down for food. In the Everglades, who's your apex predator? The alligator. Now, because of our invasive species problem that we've got going on with the python, that's a situation where we are slowly ending up with 2 apex predators. And you typically don't have 2 apex predators because there's always, to every food chain, that expression, the top of the food chain. Whenever you have that, you have ecological issues, competition that you shouldn't have, and so forth, and that could disturb the balance of the ecosystem. Your trophic levels can be seen in pyramids, in forms of pyramids. Each level is a level in that food chain. Now there are different types of pyramids that you're going to see. Primarily on the EOC, you're probably going to see this, what we refer to as the energy pyramid. But there is a pyramid that talks about biomass, the type of living mass that we have. You can count it in kilograms and so forth. And we can also do a number pyramid as well, which basically is talking about the number in terms of how many and the actual size of the organism as well. So it could go either or. The more common is your energy pyramid. And if I would venture to say which one you might see on the EOC, I would say this one. But you should be familiar with the fact that a biomass pyramid exists, and so does the numbers pyramid as well. Now, when energy is moving from one level to another, we have to concern ourselves with the first law of thermodynamics. And the first law of thermodynamics states where energy cannot be created or destroyed. It can only change from one form to another. When that plant goes through the process of photosynthesis and makes energy, it's dealing with what? Solar energy. And now when that herbivore comes and consumes that plant, the energy that he's getting is not solar energy. It is chemical energy. And from that point on, it will remain chemical energy. But producers gather solar energy and consume and use solar energy. But then from that point on, chemical energy, that solar energy is going to change into chemical energy. And then as you go on through the different consumers, it's just changing from one chemical energy to another form of chemical energy as well. So again, just letting you see that the sun is going to be the first trophic level. Energy is derived from the sun to the producer. And from the second trophic level, you're going to have your primary consumer, which is that herbivore that eats the producer or consumes it. And then you have your third trophic level has your secondary consumer, and your fourth trophic level has your tertiary consumer. Your second law of thermodynamics is stating where whenever energy is transferred, there's always going to be a loss of energy through the release of heat. Whenever you have an energy transfer, you never, under any circumstance whatsoever, you never have 100% efficiency in the transfer of energy. Even in electricity, there's always a loss of energy when you plug in to the wall. Where does it go? It releases out into the atmosphere as heat. When an animal eats another animal, in the squirming and trying to get away, it's losing some of its energy. It's burning calories at that point, trying to get away. Those are calories that the predator, that the consumer, is not going to obtain. In the chewing process, even that is losing energy that's going to evaporate out into the atmosphere. And I know what you're thinking. You're saying, well, wait a minute, Mr. Paulo, what about when a consumer swallows an organism whole? Like a shark comes by and just opens his mouth and swallows the entire fish. Doesn't even need to bite. For a few seconds, that fish is going to what? It's going to remain living inside of the body of that shark. So for those few seconds, he is losing energy. And even though it's inside the body of the shark, it's still going to be lost as heat. The shark will release it as gas out of the shark. Okay? So it's still going to be released out into the atmosphere. And that is the second law of thermodynamics. Anytime you have a transfer of energy, it's never going to be 100% efficient. There will always be a loss through the release of heat out into the atmosphere. So when one animal feeds on another, there's a loss of energy in that process. Additionally, that loss of energy occurs during respiration and movement. More and more energy is lost as you go up the trophic level. When organism number A consumes organism B, how much energy do you think he gets from organism B? Let's say, to speak in a very round number, organism B had 100 calories. Of those 100 calories, how much do you think is lost and how much do you think goes into organism A? You think it's 50-50? Okay. It's actually lost. It actually loses 90% and it actually only acquires 10%. So when, let's say, for example, a snake consumes a small lizard, and let's say, like I said, to speak in very round numbers, I'm going to say 100 calories. Let's say that lizard has 100 calories of energy in it. That snake is only going to obtain 10 calories from it. The other 90 are going to be lost in the process of death, in the process of chewing, digestion, and so forth. What that snake will actually only get as usable energy that the snake can use to do whatever, it's only going to get 10%. If that lizard had, now let's say, for example, that lizard obtained 10 calories, 10% from the lizard. Now the snake gets eaten by a large falcon. The falcon will only get 10% of that snake, and it will only get 1% of the 10% from the lizard. So when the lizard, the 10 calories from the lizard makes its way to the bird, only 1 calorie originated from that lizard will make it to the bird. And each time you go up, you always have a 90% loss of the original number. All right, real quick, let's go ahead and take this quiz. Algae at the beginning of the food chain belongs to which one of the groups of organisms listed below? Okay, the answer is C, producers. Only 10% of the energy stored in an organism can be passed on to the next trophic level. I kind of gave you the answer to that one. So of the remaining energy, some is used for the organism's life process. What happens to the rest of the energy? The answer is D, it is eliminated as heat. What is illustrated by the trophic levels in the diagram below? What do we see there? We see basically the relative number of individuals of individual organisms in each level. So what pyramid would this be? Would this be the energy pyramid? This would be the numbers pyramid, not a biomass or an energy. Now, could you pull an energy pyramid from this? Yes, you could. Now let's briefly talk about biogeochemical cycles. Carbon atoms that are in your body right now have been used in numerous other molecules for hundreds of thousands of millions of years. So there was wood that was burned 100 years ago, right? And it produced carbon dioxide into the atmosphere. Through photosynthesis, it became part of a salad that you ate yesterday. Do you believe it or not? Do you think this is true? Wood burned from 100 years ago releases carbon dioxide, and that carbon dioxide, recently made its way into this salad which you ate last night. How many of you believe that that is true? Very few of you, right? Well, actually, it is. Maybe, maybe not. But it is true. It is true. And again, these laws of conservation of matter and laws of conservation of energy tell us that. The law of conservation of matter tells us that matter cannot be created nor destroyed, only transformed. So the matter from the wood being burned 100 years ago is still going to exist. And same thing with energy. Energy cannot be created nor destroyed. It's only transferred from one form to another. So when that wood is burned and the carbon dioxide is released out into the atmosphere, it can become part of the carbon cycle and part of the water cycle, and it can make its way back down into the ground, which eventually would be pulled as nutrients for the plant that were used in that salad, and that process could take 100 years. Every time you see a plane flying up in the sky and you see it leave that long white trace that looks like a smoke, what is that? That's trace carbon. That carbon is going to slowly make its way down to Earth and become part of the atmosphere. And you know what? You're going to breathe it in. It could take years to do so, and wind patterns could shift it, and maybe it won't be to you, but it's going to be to someone. And you're going to breathe it in, and that carbon is going to enter into your body that very same way. Or it could be breathed in by another animal, which you're going to eat that animal, and that smoke that you see, which is not smoke again, it's trace carbon up there, is going to eventually make its way into your body. So the next time you're standing there and you're looking at that plane leaving that long white line across the sky, know that 50, 100 years later, or less, or more, that line could end up, inside of someone. But it is going to make its way back down here. These are the two natural laws that are the basis for the water cycle and the carbon cycle. The conservation of matter and the law of conservation of energy. Now that water cycle, our do not question today used the word transpiration. And you need to understand transpiration as part of the water cycle, the loss of water from plants. So we don't call it evaporation because water evaporates here from a body of water. But when water is lost from a plant, that's transpiration. Both make their way up to form condensation. When condensation reaches the level of saturation, it comes back down to Earth as precipitation. And eventually this is going to cycle around. I don't want to go too in depth into the water cycle, simply because, again, this is, just your understanding of how energy is going to flow. And sometimes energy flowing around will use the water cycle as a vehicle per se for energy to make its way back down. Some interesting facts about the water cycle that I think you should know. Many places on Earth have trapped water as part of Earth's fresh water supply by freezing it. Our polar ice caps, that's trapped water. That's trapped water that's considered fresh water, and it does constitute part of the Earth's water supply. Our whole issues with global warming are doing what? Are depleting this part of the Earth's freshwater supply. When temperatures rise above 0 degrees Celsius, that ice begins to melt. So when this happens on a mountain, let's say, that freshwater stream or river is going to feed that water into a lake. When the temperature at the top of the lake or the river or the stream or any body of water for that matter is at 100 degrees Celsius, that water is going to evaporate. This is water basically changing from one form to another, but cycling around as part of the water cycle. And as water evaporates and rises into the atmosphere, it'll eventually condense and then precipitate back down to the earth. Precipitation, rainwater, will fall back down. Now let's briefly talk about the carbon cycle. And I want to mention that this picture of the carbon cycle is very simple. It is missing a lot. But what it does show is where water cycle typically does what? And it goes in for the most part, one direction. The carbon cycle does not. It's a major difference between the two. Carbon takes off in multiple directions. We have carbon in the atmosphere. We have carbon in water. We have carbon in mass, biomass, trees, like for example. And we have carbon in the ground, in the lithosphere, in Earth. And carbon is going to cycle around in any one of these multiple directions. It could go from the atmosphere either. It's going to go from the atmosphere to water. It can also go from the atmosphere into biomass through the process of photosynthesis, decomposition, and respiration. From biomass, it can go back into the atmosphere. It can also go into the ground. Depending on what biomass we're talking about, it can also make its way into oceans as well. From the ground, so in other words, you can see where the arrows are pointing that the carbon cycle can basically cycle around in all these multiple directions. Carbon is found in the atmosphere, in water, in the ground, and in living organisms, including us. Some interesting facts about the carbon cycle. Carbon dioxide is in Earth's atmosphere, and during the process of photosynthesis, it combines with hydrogen to form carbohydrates in plants. We use carbohydrates as a primary source of energy. So it's going to be basically during the process of cellular respiration, it's going to move its way from stored chemical energy and broken down by organisms that consume these plants. When the organisms use the carbohydrates as energy, it gets released back into the atmosphere as carbon dioxide. We break it down in our body through cellular respiration, and then through our respiratory system, our cardiovascular system, we bring oxygen in and we release carbon dioxide back out into the atmosphere. Carbon is stored in the ocean, and many organisms use carbon to build their shells in the ocean. Fossil fuels are also a very good example of carbon. An animal or a plant dies, decomposes down into the ground by the process of that organism being buried through weathering, erosion, and so forth, and make its way down and down and down into the ground through heat and pressure. They're going to form oil, gas, and coal, are fossil fuels. Okay? And that is basically it in terms of energy flow. The next PowerPoint is population ecology. And then after that, we will cover the third PowerPoint that I have on this, which is our human interactions do to affect our ecosystems. So look for the next one to be population ecology.